All right, lecture 3 in our series is about angular momentum, and we know what linear momentum is. It's just the amount of tendency an object has to keep moving with a certain mass, with a certain speed in a direction, and angular momentum is just the same idea applied to an object that is rotating. It's measuring like how much tendency it has to keep rotating at a certain speed. And the formula for angular momentum is I, moment of inertia, times W, which is angular velocity. And to start off, moment of inertia measures how difficult it is for an object to start to spin or to stop to spin. And most of the time, we know beforehand what the moment of inertia is. It's given to us, or it's like we're supposed to memorize it into a table. And the vast majority of the time, whether it's like a disc, a ball, a rod, it's going to be like K times mr squared. K being a constant. It could be like 1/2, it could be 1, it could be 1/3, 1/12. These are different constants depending on what the object is. And the real formula for moment of inertia is that it equals the integral of m dr. And angular velocity, which is W, is just measured in radians per second, just how fast it's rotating, and this is measured in hertz, seconds to -1, but it's really radians per second, but radians doesn't have a unit. And we find this by looking at the tangential velocity, v, and we divide it by the radius. So this is pretty much it. This is the formula for angular momentum, and this is all we need to know. And similar to linear momentum, angular momentum is conserved, meaning that if there's no external force, I1 plus W1 equals I2 plus W2. And that is the key to solving most of these problems, is just plugging in the values we know into angular momentum and then seeing how we conserve it. All right, question number 3. So this question asks about a particle. It's 2 kilograms. It's moving in the straight direction along this line, y equals 4. And it's asking about the angular momentum with respect to the origin. So basically, how much angular momentum is there with respect to the origin? What's the angular momentum? Is it constant, not constant? And what is it if it is constant? So the first thing we need to know is that angular momentum equals P equals moment of inertia times angular speed, or angular velocity. And now we know that the moment of inertia of the system is not going to change. It's constant because the system's not really changing itself. So it's still going to have whatever moment of inertia it's going to have. But the angular velocity or the angular speed definitely could change. And we need to determine what that angular speed is to see if it's constant or not. So the way we do that is by looking at the change in the angle it makes with the origin. So here is the angle it makes the origin right now. We can call like this here theta. I guess that's it doesn't really matter what necessarily we call it, because we're just looking at the change in speed, but we can call this theta right here. And the way we solve for this theta right here is by taking the inverse tangent of these two ratios. And now this ratio is always going to stay 4. So we know theta equals tan inverse of 4 over whatever this length is. And we know this length right here isn't constant because this particle is moving, and it's moving at a speed of 0.8 meters per second. So we can represent this distance here as -3, because that's the starting point, minus 0.8, or minus negative, I guess would be plus 0.8 t in seconds. So we can see that this x distance is changing here, but the y distance is constant. So we have our formula for the angle theta is 4 inverse tan of 4 over -3 plus 0.8 t. So in order to calculate the angular speed, we basically, angle speed is the derivative of velocity, is the derivative of the angle. So we must take the derivative of this to find what the actual angular angular speed is in order to multiply it by the moment of inertia. However, we can see just by basic calculus knowledge that if we take the derivative of an inverse tangent of something, we're going to get like a 1 over something plus x squared, which is clearly not going to be a constant function. So we can immediately rule out that by taking the derivative of this function of angle, we're not going to get a constant angular momentum, a constant angular speed, and therefore, if the angular speed is changing all the time, then the total momentum is going to be changing, and therefore it is not constant, which is A.